Far beyond the quiet glow of our night sky, a visitor drifts, silent, ancient, and unknown. Astronomers have named it 3I Atlas, only the third confirmed interstellar object to wander into our cosmic neighborhood. But this time, there's a strange twist. Its trajectory brushes close to the red planet, Mars. So what does this mysterious traveler want with Mars? Could its path be coincidence? Or does it whisper something deeper about the mechanics of our universe? If you clicked on this video, you're in the right place. Tonight, we'll follow 3I Atlas on its silent journey, and together we'll ask the questions scientists can't yet fully answer. Tonight, we drift into a story written in starlight and whispered across the cosmic dark. Imagine, if you will, a visitor from another star system, a wanderer carrying secrets from depths we've never touched, gliding silently through our solar neighborhood, on a path that began long before our planet learned to dream. And before we step further into this story, let me pause for just a moment. I am the Sleeping Professor, your companion through these quiet journeys, a place where we explore the universe slowly, carefully, and always with wonder. Chapter 1. A soft arrival. A visitor in the dark, in the velvet hours before dawn. When most of the world sleeps, and only the night shift astronomers keep their patient vigil. Something extraordinary moves through the darkness beyond our atmosphere. It's barely more than a whisper in the data streams, a gentle anomaly that catches the eye of automated systems designed to watch for the unexpected. Picture this visitor as a faint lantern drifting along an invisible highway. Its light so dim that it takes the combined patience of telescopes and algorithms to even notice its presence. This is how most cosmic discoveries begin, not with fanfare or sudden revelation, but with the quiet persistence of human curiosity paired with mechanical precision. Our hypothetical traveler, let's call it 3I Atlas for now, moves along what astronomers call a hyperbolic trajectory. Think of it as a path that arrives from nowhere our solar system has ever touched, sweeps through our celestial neighborhood with elegant inevitability, and then continues on toward a destination we cannot imagine. It's a visitor, not a resident, carrying within its frozen heart the chemistry and story of stellar nurseries that formed when our own sun was barely a gleam in a nebula's eye. The beauty of such objects lies not just in their exotic origins, but in how they remind us that space is not empty. Stars birth clouds of ice and rock that wander for millions of years, occasionally drifting close enough to our solar campfire to be noticed by those who know how to look. These are messengers from the vast library of worlds beyond our reach. Dusty books written in languages we're only beginning to learn. As our electronic sentries register each night's harvest of positions and brightness measurements, they're participating in one of humanity's oldest activities. Watching the sky and wondering what stories the moving lights might tell. The difference now is that our tools can see so much further into the darkness, catching whispers of motion that would have been invisible to earlier generations of skywatchers. Tonight, as you settle into the rhythm of this story, let your mind's eye adjust to the cosmic dark. Feel the patient scanning of automated surveys, the gentle accumulation of data points, and the gradual emergence of a trajectory that speaks of journeys begun in stellar nurseries we may never visit. Now that our eyes have adjusted to the dark, let's gently decode the name this visitor carries. Chapter 2. Names and Numbers. Decoding 3I Atlas. There's something almost musical about how astronomers name the objects they discover. A careful poetry of letters and numbers that tells a story to those who know the code. When we speak of 3I Atlas, We're using a language that connects this hypothetical visitor to a small but growing family of cosmic wanderers. The I stands for interstellar, a designation reserved for objects that clearly originated beyond our solar system's embrace. Before 2017, this category didn't even exist in our official naming conventions. We simply hadn't confirmed any visitors from the deep void between stars. But then came one Enigma, tumbling end over end through our solar system like a cosmic cigar, followed 2 years later by 2I Borisov, a more conventional-looking comet that nonetheless carried the unmistakable signature of another star's influence. The number 3 would simply mean this is the third confirmed interstellar object. A placeholder in our story that acknowledges we're still waiting for that next visitor to announce itself. These objects earn their I designation by demonstrating what's called a hyperbolic orbit, a path so energetic that the sun's gravity cannot capture them permanently. They arrive with what astronomers call excess velocity, moving faster than any object born in our solar system ever could, carrying the kinetic signature of their alien origins. The Atlas portion of our visitor's name refers to the Asteroid Terrestrial Impact Last Alert System, a network of telescopes that scan the sky each clear night, searching for potentially hazardous asteroids, but occasionally stumbling upon far more exotic prizes. It's fitting that Atlas might be the discoverer, as this system has already found numerous comets that bear its name, each discovery adding another verse to the ongoing song of solar system exploration. But let's pause here for a gentle disclaimer. Whispered like a bedtime story caveat. 3I Atlas, as we discuss it tonight, is a thoughtful fiction, a realistic placeholder for the next interstellar visitor that will surely grace our skies someday. We use this name not to deceive, but to explore the beautiful possibilities that await us when that next cosmic wanderer does arrive, as astronomy's patient observers assure us it eventually will. The naming process itself reveals something profound about how we approach the unknown. Each designation carries within it a tiny biography. Where the object was found, what kind of path it follows, and which dedicated observers first noticed its subtle motion against the star field. These names become part of humanity's expanding vocabulary for describing our place in a galaxy filled with wandering worlds. In the international language of astronomy, these designations cross all earthly boundaries, whether spoken in English, Mandarin Arabic, or any other human tongue. 3I Atlas would carry the same meaning, a recognition that some discoveries belong not to any single nation or culture, but to our species' collective effort to understand the cosmic environment we inhabit. With a name in place, let's meet the watchful eyes that might first notice such a visitor. Chapter 3. The Eyes That Spot Wanderers. Inside Atlas, imagine a lighthouse that sweeps not the ocean's surface, but the ocean of space itself, methodically, patiently, night after night, watching for the unexpected. This is the essence of the Atlas survey, a coordinated network of relatively small telescopes that together keep watch over most of the visible sky, alert for anything that moves or changes or appears where nothing was seen before. The heart of Atlas beats in Hawaii, where two 0.5-meter telescopes scan the heavens with the dedication of lighthouse keepers. But unlike the steady beam of a maritime beacon, these instruments capture the entire accessible sky in a carefully choreographed dance, taking multiple images of each patch of darkness and then comparing them to detect the slightest hint of motion or variation. On any given night, when clouds permit and the moon doesn't wash out the faintest objects, Atlas telescopes capture hundreds of thousands of individual images. Each frame covers an area of sky roughly equivalent to holding a dinner plate at arm's length. Wide enough to survey vast territories, yet detailed enough to spot objects no larger than a city block on an asteroid hundreds of millions of miles away. The real magic happens in the quiet hum of computer processors analyzing these images. Sophisticated algorithms compare each night's observations with previous surveys, looking for the telltale signs of motion that distinguish a wandering asteroid or comet from the stationary backdrop of distant stars. Most nights, the system identifies dozens of already known objects, updating their positions and confirming their predicted paths. But occasionally, perhaps once every few months, something new appears. When Atlas spots a potential discovery, the process unfolds with the careful deliberation of a cosmic detective story. The system flags the object for human review, and experienced observers examine the candidate to ensure it's not simply a processing error, a cosmic ray hit on the detector, or the reflection of a passing satellite. But here's where the dance becomes interesting. The planets, following their own predictable orbits around the Sun, occasionally find themselves positioned along or near these hyperbolic highways just as an interstellar visitor passes through. Mars orbits the Sun at an average distance of about 228 million kilometers, taking roughly 687 Earth days to complete each circuit. This orbit intersects the ecliptic plane, the imaginary disk in which most solar system objects travel, at a location that puts Mars in the right neighborhood to potentially encounter objects following certain classes of hyperbolic trajectories. The timing doesn't have to be perfect. Gravitational encounters can be significant even when objects pass within several million kilometers of each other. The probability mathematics are fascinating in their own quiet way. While any specific close approach is unlikely, space is vast and objects are small. The growing population of interstellar visitors makes some encounters statistically inevitable over time. As our detection capabilities improve, and we discover more of these wandering messengers, the chances increase that we'll witness one of these cosmic meetings. What makes a Mars encounter particularly intriguing is the unique observational geometry it would provide. When an interstellar object passes through the inner solar system, we typically observe it from Earth's perspective, which gives us one viewpoint and limits our ability to determine certain characteristics like the object, three-dimensional shape, or the exact direction of any gas jets it might be producing. But with Mars positioned differently in its orbit, sometimes on the opposite side of the Sun from Earth, we gain the possibility of stereoscopic observations, two different viewing angles that can reveal details invisible from any single vantage point. The gravitational focusing effect of the Sun also plays a role in making Mars encounters more likely than pure chance would suggest. As interstellar objects approach our solar system, the Sun's gravity doesn't just bend their paths. It effectively concentrates them into a narrower range of trajectories than they would follow in the absence of a massive central object. This focusing effect means that objects approaching from certain directions in interstellar space are more likely to pass through the region of Mars's orbit than a random distribution would predict. The synodic timing, the alignment of Mars and an incoming object, adds another layer of elegance to the possibility. Mars completes its orbit in about 1.88 Earth years, which means that the red planet returns to any given position relative to the background stars on a predictable schedule. an interstellar object approaching along a trajectory that would bring it near Mars's orbital path, has multiple opportunities for an encounter, as Mars returns to potentially favorable positions every couple of years. Perhaps most beautifully, the mathematics of these encounters reveals that they require no special intention or targeting. They emerge naturally from the large-scale architecture of our solar system and the random distribution of interstellar objects in our galaxy's disk. Every star system likely experiences similar meetings as the debris of planetary formation and the occasional gravitational refugees from other systems wander through the space between worlds. Having traced the rails, let's see how close and how bright such a meeting might be. Chapter 6. Close Approach Scenarios. How near, how fast, how bright in the gentle mathematics of celestial encounters. Distance and geometry whisper together to determine what we might observe when worlds from different star systems briefly share the same patch of sky. For our hypothetical 3I Atlas meeting with Mars, the details of that cosmic conversation would depend on factors as delicate as the object's original trajectory and as robust as the unchanging laws of physics. Consider first the range of possible encounters. At the distant end of the spectrum, our interstellar visitor might pass Mars at a separation of several million kilometers, close by astronomical standards, but far enough that the two objects would appear as separate points of light even to our most powerful telescopes. Such a distant encounter would still be scientifically valuable, offering the chance to study how an interstellar object's behavior might be influenced by Mars's thin atmosphere or weak magnetic field, and providing the crucial stereoscopic observations that could reveal details hidden from Earth-based observers. A moderate encounter might bring the objects within 1 million kilometers of each other, roughly 3 times the distance between Earth and our Moon. At this range, the interstellar visitor would appear noticeably brighter when viewed from Mars than from Earth, simply due to the inverse square law that governs how brightness changes with distance. More importantly, instruments on Mars orbiting spacecraft would have a clear view of the object's approach and departure, potentially capturing changes in its activity level as it moves through different regions of the solar wind, or responds to varying levels of solar heating. The rare spectacular scenario would involve a truly close passage, perhaps within a few 100,000 kilometers of Mars. Such an encounter would offer unprecedented opportunities to study an interstellar object in detail, potentially revealing surface features, the structure of any gas or dust emissions, and the precise details of how the object responds to the Martian environment. The geometry would also create dramatic differences in the apparent brightness and position of the object as viewed from Earth versus Mars, providing powerful constraints on its orbit and physical properties. The speed of the encounter adds another dimension to consider. Interstellar objects typically move at tens of kilometers per second relative to the Sun, which translates to breathtaking velocity during a planetary encounter. Even a close approach to Mars would unfold over a matter of days or weeks, with the most dramatic changes in brightness and viewing geometry compressed into a much shorter period. This places a premium on rapid response and coordination between different observing platforms. Brightness calculations reveal why such encounters are so precious for science. An interstellar object that appears as a faint smudge when viewed from Earth might become bright enough for detailed spectroscopic analysis when observed from Mars's vicinity during a close approach. The improved brightness could mean the difference between detecting only the most abundant gases in the object's atmosphere and being able to measure trace species that reveal details about its formation environment and subsequent history. The phase angle, the angle between the Sun, the interstellar object, and the observer, also plays a crucial role in determining what we might see. During different portions of the encounter, Mars-based instruments would view the object from various angles relative to the Sun's illumination, potentially revealing details about the object's shape, rotation, and surface properties that would be impossible to discern from a single viewing angle. The exact geometry of a Mars encounter would remain somewhat uncertain until the event itself unfolds. Safety considerations add a sobering note to these scenarios. While the probability of a direct collision is vanishingly small, the possibility of encountering debris shed by the interstellar object requires careful planning. Spacecraft in Mars orbit would need to assess the potential dust hazard and possibly adjust their pointing or operational modes to protect sensitive instruments during the closest phases of the encounter. The uncertainty inherent in predicting these encounters adds to their scientific value. Even with months of observations to refine the orbit of an approaching interstellar object, the exact geometry of a Mars encounter would remain somewhat uncertain until the event itself unfolds. This uncertainty means that observing plans must be flexible, with instruments and mission operations teams prepared to adapt their strategies as the encounter geometry becomes more precisely known. If the view from Mars is promising, who on Mars could actually watch? Chapter 7. Mars as an observatory. Watching from the red planet Mars hangs in space like a patient sentinel, hosting an international fleet of robotic observers that have transformed our understanding of the red planet itself. But these same instruments, designed to peer down at Martian geology and atmosphere, might also serve as uniquely positioned windows for observing visitors from other star systems. Cosmic lighthouses offering a perspective unavailable from any Earth-bound observatory. The Mars Reconnaissance Orbiter, gracefully circling the planet since 2006, carries instruments that could contribute to interstellar object observations in unexpected ways. Its high-resolution imaging science experiment, HiRISE, typically focuses on capturing detailed images of the Martian surface. But this same camera possesses the precision, pointing, and high resolution that could, in principle, track a bright interstellar visitor across the Martian sky. While HiRISE field of view is narrow, designed for studying landscape features rather than surveying large areas of sky, its exceptional image quality could reveal details about an object's shape and activity that would be impossible to discern from Earth. The Mars Color Imager, or MARSI, offers a wider perspective, routinely monitoring Mars's atmosphere and weather patterns from orbit. This instrument's broad field of view and regular observing cadence make it well suited for tracking objects that move significantly across the sky over periods of days or weeks. While not designed for precision astrometry, MARSI could provide valuable context observations, showing how an interstellar visitor's apparent motion relates to Mars's atmospheric features and overall geometric relationship to the planet. MAVEN, the Mars Atmosphere and Volatile Evolutio mission, orbits Mars with instruments designed to study the planet's upper atmosphere and its interaction with the solar wind. During a close encounter with an interstellar object, these same instruments might detect subtle changes in the Martian environment caused by the visitor's passage. MAVEN imaging, ultraviolet spectrograph, could potentially observe ultraviolet emissions from gases surrounding the interstellar object, while its plasma analysis instruments might detect perturbations in the solar wind caused by the object's interaction with the interplanetary medium. The European Space Agency's ExoMars Trace Gas Orbiter brings another set of capabilities to the Martian observation platform. Its NOMAD and AXE instruments, designed to detect trace gases in Mars's atmosphere with extraordinary sensitivity, could potentially observe spectral signatures from an interstellar visitor's coma or tail. These instruments are already proving capable of detecting atmospheric constituents at concentrations of parts per trillion, sensitivity levels that might reveal subtle emissions from a nearby interstellar object that would be undetectable from Earth. Down on the Martian surface, the nuclear-powered rovers Curiosity and Perseverance carry cameras and instruments that routinely observe the Martian sky as part of their atmospheric monitoring program. While these surface-based observations are limited by Mars's thin atmosphere and the rover's earthbound perspective, more importantly, surface observations would offer a completely different geometric perspective than orbital measurements, contributing to the precise determination of the visitor's trajectory and distance. The value of Mars-based observations extends far beyond simply having another vantage point in space. The time delay for communications between Earth and Mars, ranging from about 4 minutes to over 20 minutes depending on the planet's relative positions, means that Mars-based instruments must operate with considerable autonomy during rapid observational campaigns. This independence could prove crucial during the brief, precious windows when an interstellar visitor is optimally positioned for study. Perhaps most importantly, the existing infrastructure for Mars observations provides a tested framework for rapid coordination between multiple platforms. The Deep Space Network already routinely manages communications with numerous Mars missions simultaneously, and mission operations teams have experience coordinating observations between orbiters and surface assets. This existing coordination capability could be adapted to support the rapid, flexible observing campaigns that interstellar object encounters demand. The parallax measurements possible with simultaneous observations from Earth and Mars offer scientific value that extends well beyond what either location could provide alone. By observing the same object from 2 different positions in the solar system, astronomers can directly measure its distance and refine its trajectory with extraordinary precision. These measurements would be particularly valuable for an interstellar object, where small uncertainties in the orbit translate to large uncertainties in predicting the object's behavior and optimal observing opportunities. With eyes in place, what are we hoping to learn from 3 eyes' brief lantern glow? Chapter 8. What scientists hope to learn? Composition, origins, physics. When astronomers dream of studying an interstellar visitor, their wish lists read like inventories of cosmic archaeology, each measurement a potential key to understanding not just the individual object, but the broader story of how planetary systems form, evolve, and scatter their contents into the galaxy's vast repository of wandering worlds. The most fundamental questions center on composition. What materials make up this messenger from another star? Spectroscopic analysis, the study of how the object absorbs and emits light at different wavelengths, can reveal the presence of specific molecules and atoms in the gases that surround an active interstellar comet. Water vapor, carbon monoxide, carbon dioxide, hydrogen cyanide, ammonia, and dozens of other compounds Each leave distinctive fingerprints in the spectrum of light coming from the object's coma and tail. But it's not just the presence of these molecules that matters. It's their relative abundances that tell the real story. The ratio of carbon monoxide to water vapor, for example, provides clues about the temperature conditions in the protoplanetary disk, where the object originally formed billions of years ago. Objects that condensed in the cold outer regions of their birth system should show different molecular ratios than those that formed closer to their parent star and were subsequently ejected by gravitational interactions. One of the most precious measurements would be the deuterium to hydrogen ratio in the object's water. Deuterium, a heavy isotope of hydrogen, forms under specific conditions that depend on temperature, density, and the chemical environment present during the early stages of planetary system formation. This ratio serves as a kind of cosmic birth certificate, potentially revealing not just where in its birth system the object formed, but also providing clues about the broader galactic environment where that formation took place. The dust expelled by an interstellar visitor carries its own wealth of information. Polarization measurements, studying how the dust particles scatter light in preferred directions, can reveal the size, distribution, composition, and structure of the solid grains that make up the object's nucleus. These particles represent some of the most primitive materials in the universe, preserved in the deep freeze of interstellar space for millions or billions of years after their formation. The object's rotation state offers another window into its history. How fast does it spin, and around which axis does it tumble chaotically, or does it rotate with the stable precision of a spinning top? The answers to these questions provide clues about the object's shape, internal structure, and the violence of the events that originally sent it wandering through interstellar space. A smoothly rotating object might suggest a relatively gentle ejection from its birth system, while chaotic tumbling could indicate a more catastrophic origin. Any signs of non-gravitational acceleration, the subtle deviations from a purely gravitational trajectory that reveal active outgassing, would be particularly valuable to measure from multiple viewpoints. The direction and magnitude of these forces, combined with observations of the object's brightness and spectroscopic activity, could reveal details about the location and orientation of active regions on the object's surface. This information, in turn, provides insights into the object's internal structure and the processes that drive its activity as solar heating warms its frozen surface. The broader implications of these measurements extend far beyond the study of a single object. Interstellar visitors serve as natural laboratories for testing our understanding of planetary formation processes. Or do they reveal signatures of formation environments with different temperatures, pressures, or chemical compositions? Each interstellar object also contributes to our understanding of galactic dynamics and the processes that populate interstellar space with wandering debris. How common are these objects? What types of stellar systems are most likely to eject material into interstellar space? How long do these objects survive their journey through the harsh environment between the stars? Perhaps most intriguingly, interstellar visitors offer the possibility of studying volatile materials, water, carbon dioxide, methane, and other ices that formed under conditions completely different from those present in our own solar system. These materials might preserve records of stellar nucleosynthesis processes, supernova enrichment, or other galactic chemical evolution processes that we can study in no other way. The study of complex organic molecules in interstellar objects opens even more speculative but potentially revolutionary possibilities. Do these visitors carry the chemical building blocks of life in forms that differ from those found in our own solar system? Could they provide insights into the universality or uniqueness of the chemical pathways that lead to biological complexity? To reach for those answers, we need tools ready to move quickly. Chapter 9. Dust, Gas and Plasmas. Mars meets an interstellar coma in the delicate realm where worlds briefly touch. The encounter between Mars and an interstellar visitor would unfold as a subtle conversation between different environments. The thin whisper of the Martian atmosphere brushing far against the even more tenuous gases and dust particles streaming away from our cosmic guest. The instruments aboard MAVEN, orbiting Mars with sensors designed to taste the planet's atmospheric escape to space, would find themselves in a unique position to eavesdrop on this celestial dialogue. Often that's as miles, ceased Alt-wide the spacecraft's neutral gas and ion mass spectrometer, normally sampling the rarefied gases of Mars's upper atmosphere, might detect trace amounts of exotic molecules liberated from the interstellar visitor. Water vapor, carbon monoxide, or other volatiles never before measured in the Martian environment. Even more intriguingly, MAVEN plasma instruments could observe how the solar wind, the stream of charged particles flowing outward from the Sun, interacts with the interstellar object's ionized coma, Yi. When ultraviolet light from the Sun strikes gas molecules in the comet's atmosphere, it strips away electrons, creating a population of ions that become entrained in the solar wind's magnetic field. These pickup ions, as they're called, create distinctive signatures that MAVEN's Solar Wind Electron Analyzer and Solar Wind Ion Analyzer are exquisitely designed to detect. The interstellar visitor's ion tail, that graceful streak of charged particles swept back by the solar wind, might interact with Mars's own magnetic environment in subtle but measurable ways. Mars lacks a global magnetic field like Earth's, but it does possess localized magnetic anomalies in its crust, remnants of an ancient dynamo that died billions of years ago. As the comet's ion tail sweeps past these magnetic features, it could create small disturbances detectable by MAVEN magnetometer, providing insights into both the visitor's activity level and the structure of Mars's residual magnetic field. The ExoMars Trace Gas Orbiter brings another layer of sensitivity to this investigation. Its instruments, capable of detecting atmospheric trace gases at concentrations measured in parts per trillion, might observe temporary enhancements in Mars's atmospheric composition as the planet passes through the rarefied outer reaches of the interstellar object's coma. Even if these enhancements are subtle, lasting only hours or days, they could provide valuable constraints on the visitor's outgassing rate and composition. The precedent for such observations already exists in our exploration of Mars. In October 2014, Comet Siding Spring passed within about 140,000 kilometers of Mars, closer than any comet had ever been observed to approach a planet. The International Fleet of Mars Orbiters coordinated their observations to study both the comet itself and its effects on the Martian environment. The results revealed subtle but measurable changes in Mars's upper atmosphere, demonstrating that even brief encounters between worlds can produce detectable signatures. During the Siding Spring encounter, mission controllers took the precaution of orienting spacecraft to use Mars itself as a shield against potentially hazardous dust particles from the comet's tail. This protective ballet demonstrated both the international cooperation possible in Mars exploration and the careful balance between scientific opportunity and spacecraft safety that such encounters require. An interstellar visitor would likely present even more exotic interaction signatures than siding spring, simply because of its alien origins, the isotopic ratios of gases in its coma, the size distribution of dust particles in its tail, and the chemical composition of both could all differ significantly from the solar system materials that Mars-orbiting spacecraft have previously encountered. The timing of such an encounter would be crucial for maximizing scientific return. Different phases of the approach and departure would offer different observational opportunities. The approach phase might reveal how the interstellar object's activity changes as it moves deeper into the solar system's environment, while the departure phase could show how quickly the interaction signatures fade as the visitor moves away from Mars and back toward interstellar space. The thin Martian atmosphere itself would serve as a detector for the encounter, potentially showing small changes in density, composition, or dynamics as it interacts with the interstellar visitor's extended atmosphere. These changes would likely be subtle, measurable only with the most sensitive instruments, but they could provide unique insights into the physical processes occurring during this type of cosmic encounter. Perhaps most beautifully, the entire interaction would represent a direct physical connection between Mars and materials from another star system, atoms and molecules that formed in a completely different stellar environment, carried across the light years, and finally coming into contact with a world in our own solar neighborhood. In that moment of interaction, however brief, Mars would literally taste the chemistry of another star's family of worlds. If Mars can listen, Earth can move, perhaps even to intercept. Chapter 10. Ready on the Shelf. Comet interceptor and rapid response ideas. While Mars offers a patient platform for cosmic observation, the dream of actually reaching out to touch an interstellar visitor demands a different kind of preparation. Spacecraft designed not just to watch, but to travel. To intercept, to gather samples and measurements from distances measured in kilometers rather than millions of kilometers. The European Space Agency's Comet Interceptor mission represents the most concrete step toward this goal, embodying a philosophy of cosmic readiness that acknowledges we cannot predict exactly when or where the next great opportunity will arise. Rather than targeting a specific comet known years in advance, Comet Interceptor will park itself at the L2 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, in the direction away from the Sun. This parking orbit at L2 provides several strategic advantages for intercepting unexpected targets. The spacecraft will be positioned outside Earth's gravitational well, reducing the energy required to depart for an intercept mission. It will have an unobstructed view of the solar system's outer regions, where new objects are most likely to be discovered as they approach the Sun. And it will be able to communicate continuously with Earth, without the day-night cycle that limits ground-based observations. The mission's design reflects the harsh realities of interstellar object encounters. Opportunities are brief, targets are unpredictable, and the physics of orbital mechanics leaves little room for error. Comet Interceptor is actually 3 spacecraft in one, a main probe and 2 smaller subprobes that can separate to observe their target from multiple angles simultaneously. This multi-point approach maximizes the scientific return from a single, irreplaceable encounter. The concept extends beyond individual missions to encompass a broader philosophy of rapid response space science. Traditional planetary missions require years or decades of planning, with launch opportunities determined by the predictable dance of planetary alignments. But interstellar visitors operate on their own schedule, offering opportunities that must be seized quickly or lost forever. Project Lyra, a concept study led by researchers at the European Space Agency and other institutions, has explored the technical challenges of intercepting Oumuamua-like objects using existing or near-future technology. Their studies reveal that while such missions are technically possible, they require spacecraft capable of extremely high velocity changes. Delta V, the Jupiter Gravity Assist, emerges as a crucial technique in these rapid response mission concepts. By flying past Jupiter at precisely the right time and trajectory, a spacecraft can use the giant planet's gravitational field to accelerate to speeds that would be impossible to achieve with chemical propulsion alone. This gravitational slingshot effect could potentially enable intercept missions to catch up with interstellar objects, even after they've passed through the inner solar system and begun their journey back toward interstellar space. Ground-based telescopes also play crucial roles in rapid response scenarios. Target of opportunity programs on major observatories like the James Webb Space Telescope. The upcoming extremely large telescopes and radio interferometer arrays like ALMA allow astronomers to quickly redirect their instruments toward unexpected discoveries. These programs recognize that some of the most scientifically valuable observations cannot be planned years in advance, but must respond to the universe's own schedule of revelations. The coordination required for rapid response interstellar object studies extends across national boundaries and institutional division. When 2I Borisov was discovered, the international astronomical community demonstrated this coordination capability, with observatories worldwide contributing observations that built a comprehensive picture of the object's properties and behavior. Future encounters will likely require even more sophisticated coordination, potentially involving space missions, ground-based telescopes, and Mars-based observations working in concert. Rideshare opportunities and small-sat technologies offer promising pathways for reducing the cost and complexity of rapid response missions. Small spacecraft, weighing tens rather than thousands of kilograms, can be deployed more quickly and at lower cost than traditional planetary missions. While they cannot carry the full suite of instruments possible on larger missions, they can provide crucial measurements during the brief windows when interstellar objects are accessible to study. The piggyback approach offers another possibility: designing small interstellar interceptors that could be carried as secondary payloads on missions with other primary objectives. These standby interceptors could remain dormant for years, activated only when a suitable target appears and an intercept trajectory becomes possible. But could we do something similar starting from Mars itself? Chapter 11. Could we intercept from Mars? Concepts and Delta V. The red planet hangs in space like a cosmic stepping stone, positioned at a distance from the Sun that could, under the right circumstances, serve as a launching point for interstellar visitor encounters that would be impossible to achieve from Earth alone. The mathematics of orbital mechanics whisper intriguing possibilities. When we consider Mars not just as a destination, but as a departure point for even more ambitious journeys, the fundamental advantage Mars offers for interstellar intercept missions lies in its orbital energy. Mars travels around the Sun at an average speed of about 24 kilometers per second, compared to Earth's 30 kilometers per second. While this makes Mars seem slower, the key insight is that objects seeking to escape the solar system entirely, as any interstellar intercept mission must do, benefit from starting their journey from a location that already possesses significant orbital velocity in the desired direction. The escape velocity from Mars's gravitational influence is only about 5 kilometers per second, compared to Earth's 11.2 kilometers per second. This means that a spacecraft launched from Mars orbit needs to achieve less additional velocity to break free from planetary gravity and begin its journey toward an interstellar target. The savings in required delta V, the total velocity change needed for the mission, can be substantial, potentially making the difference between a mission that's technically feasible and one that exceeds the capabilities of any realistic propulsion system. The timing considerations for Mars-launched intercept missions add layers of complexity and opportunity. Mars's orbital period of about 687 Earth days means that the planet returns to any given position relative to the background stars on a predictable schedule. For an interstellar object following a specific trajectory, there might be multiple launch windows from Mars as the planet moves through different phases of its orbit, each offering slightly different intercept geometries and energy requirements. The concept of Mars-orbiting motherships deploying smaller interceptor spacecraft offers an elegant solution to some of these challenges. A larger spacecraft, already positioned in Mars orbit for other scientific purposes, could carry one or more small intercept probes designed for rapid deployment when an opportunity arises. These probes could be simple, single-purpose vehicles optimized for high-speed flyby observations, rather than the multi-year cruise phases that characterized traditional interplanetary missions. The gravitational assist opportunities available from Mars add another dimension to intercept mission planning. A spacecraft launched from Mars could potentially use the planet's own gravity well to gain additional velocity, similar to how missions from Earth use lunar or planetary gravity assists to reach higher speeds. The timing and geometry of such maneuvers would need to be planned carefully, but they could provide crucial additional delta V for reaching high-velocity interstellar targets. Communication considerations present both challenges and opportunities for Mars-launched intercept missions. The existing deep space network infrastructure already supports communications with Mars missions, providing a tested framework for maintaining contact with spacecraft operating in the Mars vicinity. However, an intercept probe traveling at high speed toward an interstellar target would quickly move beyond the range of Mars-based relay communications, requiring either direct Earth communication capability or sophisticated autonomous operation. The lead time requirements for Mars-based intercept missions create interesting trade-offs between responsiveness and capability. A small, simple interceptor could potentially be designed and deployed within months of an interstellar object's discovery, taking advantage of Mars's position to achieve an intercept that would be impossible from Earth. However, such rapid deployment would necessarily limit the sophistication of the scientific instruments and the complexity of the mission design. The infrastructure requirements for supporting Mars-based intercept missions extend beyond individual spacecraft to encompass the broader ecosystem of Mars exploration. Regular cargo deliveries to Mars, improved in-situ resource utilization capabilities, and expanded communication networks would all contribute to making Mars a more viable launching point for ambitious interstellar missions. Perhaps most intriguingly, Mars-based intercept missions could take advantage of the planet's position during specific phases of its orbit to achieve intercept geometries that would be completely impossible from Earth. When Mars is positioned on the opposite side of the Sun from Earth, it offers a fundamentally different launching direction that could enable intercepts with objects approaching from certain regions of the sky. The Delta-V budgets for such missions, while challenging, fall within the realm of existing or near-future propulsion technologies. Ion propulsion systems, which generate small but continuous thrust over long periods, could potentially accelerate small interceptor spacecraft to the high velocities required for interstellar object encounters. Solar sails, which gain momentum from sunlight pressure, offer another low-mass propulsion option that could be particularly effective for missions launched from Mars's reduced gravitational environment. If we could pack a quick traveler, what instruments should it carry? Chapter 12. The Dream Instrument Suite. What to pack for 3I in the poetry of space mission design? Every gram of mass carries with it both possibility and compromise. When imagining the perfect scientific payload for an interstellar visitor encounter, whether launched from Earth, Mars, or anywhere else, we must balance the dreams of discovery against the harsh realities of velocity budgets, power limitations, and the brief, precious nature of the observational opportunity itself. The camera system would anchor any interstellar intercept mission, serving as both the primary scientific instrument and the navigator that guides the spacecraft to its target. A dual-camera design offers the best compromise between capability and simplicity. A narrow-angle camera optimized for high-resolution imaging of the target's nucleus and surface features, paired with a wide-angle camera designed to capture the full extent of any coma or tail structures. These cameras would need to operate under extreme conditions, potentially imaging an object moving at relative speeds of tens of kilometers per second, requiring exposure times measured in milliseconds to avoid motion blur. Fast, radiation-hardened shutters would be essential, along with autonomous tracking capabilities that could predict the target's motion and adjust pointing in real time as the encounter unfolds. A compact spectrometer would provide the key to unlocking the interstellar visitor's chemical secrets. Covering the ultraviolet, visible, and near-infrared portions of the electromagnetic spectrum, such an instrument could identify the molecular fingerprints of water vapor, carbon monoxide, carbon dioxide, and dozens of other compounds in the object's coma. The spectrometer would need to be lightweight and robust, capable of rapid data acquisition during the brief window when the spacecraft passes closest to its target. For dust analysis, a time-of-flight mass spectrometer offers the possibility of directly sampling and analyzing the solid particles streaming away from the interstellar object. As dust grains impact the instrument's detector at high velocity, they vaporize and ionize, creating characteristic signatures that reveal their elemental composition. This type of in-situ analysis has been successfully demonstrated on missions like Cassini and Stardust, providing ground truth for remote observations of dust properties. A polarimeter, an instrument that measures how dust particles scatter light in preferred directions, could reveal crucial information about the size distribution, shape, and composition of solid grains in the object's coma and tail. This data complements the direct sampling capabilities of a mass spectrometer, providing statistical information about the broader population of particles that the spacecraft cannot directly intercept. Thermal infrared capabilities would allow the mission to measure the temperature of the interstellar visitor's nucleus, providing constraints on its thermal properties and heat capacity. These measurements, combined with observations of how the object's activity changes as it moves through different distances from the Sun, could reveal details about the composition and structure of subsurface ices and the processes that drive the object's observed activity. The challenge of autonomous operation cannot be overstated for an interstellar intercept mission. Communication delays, measured in minutes or hours even for Mars-launched missions, mean that the spacecraft must be capable of executing its observational sequence without real-time human guidance. The instrument suite must include sophisticated onboard processing capabilities that can recognize the target, track its motion, prioritize observations based on rapidly changing conditions, and adapt to unexpected discoveries as they unfold. Power considerations drive many aspects of instrument design for such missions. Solar panels become less effective at large distances from the Sun, and battery systems must be sized to support intensive operations during the brief encounter phase. Radioisotope thermoelectric generators, while adding mass and complexity, could provide the consistent power source needed for sophisticated instrument operations throughout the mission. Data storage and transmission capabilities must balance the desire to capture farcical measurement against the limitations of communication systems operating across interplanetary distances. Onboard data processing and compression become crucial for maximizing the scientific return from limited downlink opportunities. The spacecraft might need to make autonomous decisions about which observations are most valuable and prioritize them for transmission back to Earth. Dust shielding presents both an engineering challenge and a scientific opportunity. While the spacecraft's instruments must be protected from potential impacts with high-velocity dust particles, the impacts themselves could provide valuable scientific data about the size and velocity distribution of particles in the interstellar object's environment. Dedicated dust detectors could monitor the impact environment throughout the encounter. The instrument suite would also need to include precision timing systems to correlate observations with the spacecraft's trajectory and the target's behavior. When every second of the encounter provides unique scientific opportunities, precise time tagging of observations becomes crucial for later analysis and correlation with remote observations from Earth and Mars. Flexibility in instrument operation becomes particularly important, given the uncertainties inherent in interstellar object encounters. The target's brightness, activity level, and behavior cannot be predicted with certainty before the encounter begins. Communication protocols become particularly important during interstellar object encounters, where rapid changes in observational circumstances require coordinated responses from multiple missions and ground-based observatories. Clear, standardized procedures for sharing safety-critical information, such as updates to the object's trajectory or activity level, help ensure that all participants can make informed decisions about their level of participation in observational campaigns. The international nature of Mars exploration adds diplomatic dimensions to safety and ethical consideration. Spacecraft and instruments from multiple nations and space agencies operate in the Mars system, requiring coordination mechanisms that transcend national boundaries when responding to rapidly evolving situations like interstellar object encounters. The existing frameworks for Mars exploration provide models for such coordination, but they would need to be adapted to the unique circumstances of interstellar visitor studies. Public communication about interstellar object encounters carries its own ethical dimensions. The excitement and novelty of such events create opportunities for misunderstanding or misrepresentation that could undermine public confidence in space science. Clear, accurate communication about both the opportunities and limitations of such encounters helps build the public understanding and support that enables continued space exploration. The long-term perspective on safety and ethics recognizes that interstellar object encounters will become more common as our detection capabilities improve and our presence in the solar system expands. The protocols and principles we establish for early encounters will shape how humanity approaches these opportunities for decades to come. Building frameworks that balance scientific ambition with safety, environmental protection, and ethical responsibility creates foundations for the expanded cosmic exploration that future generations will inherit. Perhaps most fundamentally, encounters with interstellar visitors remind us that we are participants in a galaxy-wide community of stellar systems, each producing and exchanging materials with the broader galactic environment. Our responsibilities as cosmic citizens include approaching these exchanges with the humility, care, and respect that such profound connections deserve. Held safely, the encounter becomes a teacher, just as our first visitors were. Chapter 14. Lessons from Oumuamua and Borisov. Similarities and surprises. The gentle teachers that first introduced us to the concept of interstellar visitors left behind lessons that shimmer with both familiarity and strangeness, patterns that help us anticipate what future encounters might offer, and surprises that remind us how much we still have to learn about the space between the stars. Oumuamua's most profound lesson was about the power of the unexpected. When first detected by the Pan-STARRS survey in October 2017, it initially appeared to be just another asteroid from our own solar system's collection of small bodies. Only as more observations accumulated did its true nature become clear. This was something genuinely alien, following a hyperbolic trajectory that spoke of origins in the depths of interstellar space. The object's unusual shape, elongated like a cosmic needle, or perhaps flattened like a cosmic pancake, challenged our assumptions about how small bodies form and evolve. Most asteroids and comets in our solar system are roughly spherical or only modestly elongated, shaped by their own gravity and the gentle processes of accretion and collision over billions of years. Oumuamua's extreme aspect ratio suggested formation processes or evolutionary histories that we hadn't previously considered. But Oumuamua's most enduring mystery lies in its subtle acceleration away from the Sun, a deviation from pure gravitational motion that suggests some form of outgassing or other non-gravitational force. Yet, despite intensive observations with telescopes around the world and in space, the object showed no visible signs of the gas or dust emission that typically reveals cometary activity. This disconnect between the evidence for outgassing and the absence of observable emissions sparked scientific debates that continue today. The leading explanation involves the sublimation of extremely pure hydrogen ice from the object's surface, a process that would create the observed acceleration while producing emissions too faint to detect with existing instruments. Alternative hypotheses have ranged from exotic ice compositions to more speculative possibilities involving solar radiation pressure acting on an unusually shaped object. Each explanation carries implications for our understanding of interstellar object properties and origins. Wa sai preval zire wa ive. 2. Borisov offered a more familiar but equally valuable perspective on interstellar visitors. Discovered by Crimean amateur astronomer Gennady Borisov in August 2019, this second confirmed interstellar object behaved much more like the comets we know from our own solar system. Izen D sa ni D sa fari. As it approached the Sun, Borisov developed a clearly visible coma and tail, making it accessible to the full range of astronomical techniques used to study active comets. The wealth of observations possible with Borisov revealed both similarities and differences compared to solar system comets. Its spectrum showed the familiar signatures of water vapor and hydrogen cyanide that characterize cometary activity, but with notable differences in the ratios of different molecules. Most significantly, Borisov's coma contained unusually high concentrations of carbon monoxide relative to water, a signature suggesting formation in an environment colder than the outer regions of our own solar system. The dust properties of Borisov's coma and tail also show distinctive characteristics. Polarization measurements revealed dust grains with properties similar to those found in solar system comets, but with subtle differences that suggested variations in the formation or processing environment. These measurements provided the first direct information about solid materials from another stellar system, opening new windows into the diversity of planetary formation processes across the galaxy. Early observations of any new object carry significant uncertainties. Atmospheric turbulence, instrumental limitations, and the inherent difficulty of measuring precise positions for faint, point-like sources all contribute noise to the fundamental signal. Statistical techniques help separate the true motion from this observational scatter, but the process requires patience and accumulating evidence. As observations accumulate over days and weeks, the mathematical machinery of orbit determination begins to reveal the object's true trajectory. For interstellar visitors, this process is complicated by the hyperbolic, rather than elliptical, nature of their orbits. Traditional asteroid and comet orbits are ellipses, closed curves that bring objects back to the same regions of space on predictable schedules. But interstellar objects follow hyperbolas, open curves that arrive from infinity and depart toward infinity, never to return. The mathematics of hyperbolic orbits requires 6 fundamental parameters to fully describe the object's motion: the semi-major axis, eccentricity, inclination, longitude of the ascending node, argument of periapsis, and time of periapsis passage. Each of these parameters encodes specific information about the object's trajectory, its orientation in space, its speed, and the timing of its closest approach to the Sun. The eccentricity deserves special attention for interstellar objects. All bound orbits in the solar system have eccentricities less than 1.0, while interstellar visitors possess eccentricities greater than 1.0, with the precise value determining the object's hyperbolic excess velocity, the speed it would maintain even at infinite distance from the Sun. This excess velocity serves as a fossil record of the object's journey through interstellar space, carrying information about its origins and the galactic environment through which it has traveled. Least squares, fitting techniques provide the mathematical framework for extracting orbital parameters from observational data. These methods minimize the differences between predicted and observed positions, finding the set of parameters that best explains the accumulated measurements. As more observations become available, the uncertainties in these parameters shrink, and predictions of the object's future position become increasingly reliable. But interstellar objects often complicate this process through non-gravitational accelerations. Subtle deviations from purely gravitational motion caused by outgassing as solar heating warms the object's surface. These accelerations are typically small, amounting to changes in velocity measured in centimeters per second per day. But they accumulate over time and can significantly affect trajectory predictions. The standard approach for handling non-gravitational forces involves adding 3 additional parameters, A1, A2, and A3, to the orbital solution. These parameters describe accelerations in the radial, transverse, and normal directions relative to the object's orbital plane. The A1 parameter typically dominates, representing the rocket-like effect of gas jets preferentially directed away from the sun-facing hemisphere of the object. Covariance ellipsoids provide a visual representation of the uncertainties in orbital predictions. These 3-dimensional mathematical constructs show the range of possible positions where the object might be found at any given time, accounting for the propagated uncertainties in all the orbital parameters. As observations accumulate and the orbit becomes better determined, these uncertainty ellipsoids shrink, allowing increasingly precise predictions of future positions. The parallax effect becomes particularly valuable for interstellar object studies, when observations are available from multiple locations in the solar system. By observing the same object simultaneously from Earth and Mars, astronomers can directly measure its distance through geometric triangulation. This distance information provides powerful constraints on the orbital solution, often reducing uncertainties far more rapidly than would be possible from observations from a single location. Real-time orbit determination requires sophisticated software systems that can rapidly process new observations and update trajectory prediction. The Minor Planet Center maintains global databases and processing pipelines that can incorporate new measurements within hours of their submission, providing updated ephemerides, predicted positions as functions of time, to observers worldwide. The computational challenges multiply when multiple objects require simultaneous tracking, or when observations are contaminated by systematic errors that must be identified and corrected. Robust statistical techniques help identify outlying measurements that might skew the orbital solution, while Monte Carlo methods provide estimates of how uncertainties in individual measurements propagate into uncertainties in derived parameters. For mission planning purposes, orbit determination must extend beyond simply predicting where an object will be to estimating the uncertainties in those predictions. Spacecraft navigation requires confidence intervals on target positions, while ground-based observing campaigns need to know how precisely telescopes should be pointed to acquire their targets. These requirements drive the development of increasingly sophisticated uncertainty analysis techniques. So once we can see the path, we can rehearse possibilities. Chapter 16. Forecasting the Unfamiliar. Simulations and community coordination. The art of preparing for cosmic encounters that have never happened before requires a delicate blend of theoretical modeling, computational simulation, and human coordination, a process that transforms mathematical predictions into coordinated action across continents, institutions, and the vast infrastructure of modern astronomy. Monte Carlo simulations provide the computational foundation for encounter planning, generating thousands of possible scenarios based on the statistical uncertainties in the interstellar objects, trajectory, and properties. Each simulation run explores a slightly different version of the encounter, varying the object's exact path, its activity level, its brightness, and the precise geometry of its closest approach to Mars. Together, these simulations map out the full range of possibilities, helping mission planners identify the most likely scenarios while preparing for outlying cases that might otherwise catch them unprepared. The brightness modeling presents particularly interesting challenges, as it must account for factors ranging from the object's intrinsic reflectivity to the complex ways that solar heating drives gas and dust emission from its surface. Temperature-driven outgassing models predict how the object's activity should change as it moves closer to or farther from the Sun, while scattering models estimate how efficiently the resulting dust cloud will reflect sunlight back toward observers. These models must also account for the viewing geometry, the angles between the Sun, the interstellar object, and various observing platforms. The same object can appear dramatically brighter or fainter depending on whether it's observed at full phase Sun behind the observer. For an encounter involving Mars, these geometric considerations become even more complex, as different instruments view the object from different angles simultaneously. Dust hazard simulations add another layer of modeling complexity, particularly important for protecting valuable spacecraft during close encounters. These simulations track the trajectories of particles ejected from the interstellar object, predicting their density and velocity distribution in different regions around the encounter geometry. The lessons learned from these exercises inform the development of improved coordination procedures and help identify potential failure points before they occur in actual encounters. And if this one slips away, there will be another dawn. Chapter 17. If not this visitor, then the next. The long game in the patient philosophy of cosmic discovery. Individual opportunities matter less than the accumulating infrastructure of capability, knowledge, and readiness that transforms rare chances into routine achievements. Even if our hypothetical 3-eye atlas never materializes, if it remains forever a thought experiment in the pages of this gentle story, the preparations we make and the systems we develop serve the deeper purpose of positioning humanity to greet whatever visitors the galaxy eventually sends our way. The statistics of interstellar object discovery paint a picture of accelerating opportunity. When Oumuamua first appeared in 2017, it represented a category of cosmic phenomenon that existed more in theory than in practice. By 2019, Borisov's arrival had doubled our sample size and begun to reveal the diversity we should expect from such visitors. Current estimates suggest that several interstellar objects may pass through the inner solar system each year, with most remaining undetected due to the limitations of existing surveys. But those limitations are rapidly evolving. The Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, will survey the entire visible sky every few nights, with unprecedented depth and precision. This facility alone is expected to discover dozens of interstellar objects each year, transforming them from rare curiosities into a regular component of solar system astronomy. Other next-generation surveys, both ground-based and space-based, will add to this flood of discoveries. The infrastructure that endures extends far beyond individual telescopes to encompass the entire ecosystem of detection, analysis, and response capabilities. Automated data processing pipelines that can identify moving objects in real time, rapid orbit determination systems that can characterize trajectories within hours of discovery, and international communication networks that can coordinate follow-up observations across continents and time zones. All of these capabilities serve every future discovery, not just the next one. The institutional frameworks for rapid response mature with each exercise and each actual encounter. Nandli. Fala. Faza. The procedures developed for coordinating observations of Oumuamua and Borisov provide templates that can be adapted and improved for future visitors. The lessons learned about the challenges of international coordination, the bottlenecks in data processing and distribution, and the optimal strategies for maximizing scientific return from brief observing windows, all accumulate into an institutional memory that makes future responses more effective. Elarijza was Bucknell, Sa, the Day. Space mission concepts like Comet Interceptor represent a philosophical shift toward preparedness rather than prediction. Rather than designing missions around specific pre-selected targets, these concepts embrace uncertainty and flexibility, positioning spacecraft and instruments to respond quickly when unexpected opportunities arise. This philosophy recognizes that the universe operates on its own schedule, offering treasures that cannot be anticipated years in advance. The technology development, driven by interstellar object studies, benefits the broader space science community in ways that extend far beyond any individual mission or discovery. High-speed imaging systems, compact spectrometers, autonomous navigation algorithms, and rapid response communication protocols all find applications in other areas of space exploration. The technical challenges posed by Interstellar Visitor encounters push instrument and spacecraft designers toward solutions that enable new classes of missions and discoveries. Perhaps most importantly, the study of interstellar objects feeds into humanity's growing understanding of our place in the galactic community. Each visitor provides data points for understanding the processes that populate interstellar space with wandering debris, the timescales over which material exchanges between stellar systems, and the chemical evolution of the galaxy as recorded in the compositions of objects that have traveled between the stars. The long game also encompasses the educational and inspirational value of interstellar visitor encounters. These events capture public imagination in ways that connect cosmic-scale phenomena to human curiosity and wonder. Each encounter provides opportunities to communicate the methods and excitement of scientific discovery, helping build the public understanding and support that enables continued investment in space exploration and astronomical research. The cadence of discovery improves year by year, but so does our capacity to make the most of each opportunity. Better telescopes, more sophisticated analysis techniques, improved international coordination, and more flexible mission concepts all contribute to an accelerating capability that transforms brief, precious encounters into comprehensive scientific investigations. The philosophy of readiness that guides this long-term approach recognizes curiosity as a nightly ritual, a commitment to watching, wondering, and preparing for whatever revelations the cosmos might offer. This commitment operates at multiple timescales simultaneously. The immediate response to breaking discoveries, the medium-term development of improved capabilities, and the long-term vision of humanity as an active participant in the galactic exchange of materials and information between stellar systems. In this larger context, whether any specific visitor arrives becomes less important than maintaining the infrastructure, skills, and perspective that allow us to recognize and respond to cosmic opportunities whenever they appear. The true success lies not in any individual discovery, but in building a civilization that remains perpetually ready to learn from whatever teachers the universe provides. So, in the quiet before sleep, what does such a traveler really want with Mars? Chapter 18. A Gentle Farewell. What three Atlas wants with Mars as our story draws toward its close? Let us pause to consider the strange poetry of cosmic desire. Not the anthropomorphic wanting of consciousness and intent, but the deeper wanting written into the fabric of space-time itself. The gravitational longing that draws objects along paths, determined by mass, energy, and the patient mathematics of celestial mechanics. Our hypothetical 3 Asus wants nothing in the way humans understand wanting. It carries no purpose beyond the trajectory determined by its initial conditions and the gravitational fields through which it travels. Its path toward Mars is not chosen but calculated, not intended but inevitable, the result of forces and equations that operate with perfect indifference to the objects they govern. Yet, in this mathematical wanting lies a beauty that transcends any conscious desire. The interstellar visitor wants to follow the hyperbolic. Every point along its trajectory represents the optimal balance between its intrinsic velocity and the gravitational pulls of the Sun, planets, and all the other massive objects that populate our cosmic neighborhood. The path it traces through space is the only path it can take, given the initial conditions of its arrival and the laws of physics that govern motion in gravitational fields. In approaching Mars, 3I Atlas wants to exchange information, not consciously, but through the fundamental processes that govern how objects interact across the vacuum of space. The gravitational field of Mars will subtly deflect the visitor's trajectory, while the visitor's own gravitational field will produce an equally subtle response in Mars's motion. These effects are tiny, measurable only with the most precise instruments, but they represent a genuine physical dialogue between worlds separated by millions of years and light years of evolutionary history. The visitor's relationship with light carries its own form of cosmic wanting. As solar photons strike its surface, they deliver energy that drives sublimation of surface ices and the creation of the gossamer atmosphere that surrounds active interstellar objects. This process wants to reach equilibrium, a balance between the energy input from sunlight and the energy carried away by escaping gases and dust. Mars provides a unique vantage point for observing this equilibrium as it adjusts to the changing conditions of the inner solar system. Mars, in its role as cosmic observer, offers what the visitor needs most: a patient witness to its brief passage through our stellar neighborhood. The red planet provides a second perspective, a stereoscopic companion to Earth-based observations that can reveal the three-dimensional structure and behavior of the interstellar object in ways impossible from any single viewpoint. In this sense, Mars serves as humanity's extended eye, positioned to see what our home planet cannot. The gravitational conversation between Mars and the interstellar visitor extends beyond their immediate encounter to encompass the broader galactic context in which both objects exist. The visitor carries within its trajectory and composition the signature of processes that operated in its birth stellar system billions of years ago. Mars, with its geological record of climate change and atmospheric evolution, provides a comparative perspective on planetary processes that helps us understand the diversity of possible outcomes for rocky worlds orbiting other stars. Perhaps most poetically, the encounter wants to remind us of the temporary nature of all cosmic arrangements. The interstellar visitor is just passing through, destined to continue its journey into the outer solar system and eventually back to the interstellar void from which it came. Mars will continue its patient orbit long after the visitor has faded beyond the reach of our telescopes. But for the brief moment of their cosmic meeting, these two very different objects share the same patch of sky, the same gravitational environment, the same bath of solar radiation. These des Mupui Ververischung Verwide Gation and Marked. The traces left by such encounters persist long after the objects themselves have moved on. The slight deflection in the visitor's trajectory carries forward the gravitational signature of its meeting with Mars. The data recorded by Mars-orbiting instruments becomes part of humanity's permanent archive of interstellar object observations. The theoretical understanding, developed through modeling their interaction, contributes to our broader comprehension of how small bodies behave in planetary environments. In the deepest sense, 3I Atlas wants to teach us about connection, the way that objects separated by vast distances and times can still influence each other through the fundamental forces that govern cosmic behavior. Its passage near Mars demonstrates that no object in the universe is truly isolated, that every piece of matter participates in the grand gravitational democracy that binds galaxies, stellar systems, and individual worlds into a single interconnected cosmic community. As our gentle visitor fades into the darkness beyond Mars's orbit, trailing ions and dust that catch the last whispers of sunlight, it leaves behind more than scientific data. It leaves a reminder that we live in a universe where worlds routinely exchange material, where the chemistry of one stellar system can journey across the light years to tell its story to inhabitants of another system, and where the patient observation of rare events can reveal the fundamental processes that shape the cosmos on scales both tiny and vast. The red planet dims behind our departing visitor, a russet point of light that will continue its faithful orbit long after 3I Atlas has rejoined the river of objects flowing between the stars. In that fading glow lies the promise of future encounters, future opportunities to witness the gentle conversations that unfold when worlds from different families meet briefly in the darkness and share their stories written in light. On Mars, models suggest that meteoric smoke can influence the formation of very high-altitude CO2 ice clouds and, over weeks to months, settle downward with the planet's slow atmospheric circulation. This is where memory stretches from hours to seasons. If 3I's dust load is modest, its meteoric smoke will be folded into the steady background, created by routine micrometeoroids. But if the flux is elevated, if the pass happens to graze Mars with a denser tail, the additional smoke could thicken the high-altitude cloud population for a while, a barely perceptible frosting. Instruments like MRO Mars Climate Sounder and future limb-sounding cameras can catch such clouds as hazy veils against the cold sky. The story would be statistical rather than dramatic. A small bump in occurrence, a shift in altitude, a delicate change in particle size, inferred from how the clouds absorb and emit. These changes would not shout 3I's name, but in combination with ionospheric signatures and timing, they could whisper the same sentence. The surface may keep its own record, especially in the polar regions. Each Martian winter, carbon dioxide condenses out of the air and lays down a seasonal frost that is later sublimed back into the atmosphere in spring. Think of each winter as adding a single sheet to a thin scrapbook. If 3I's dust arrives during the cold season, some fraction of those particles, metal-rich, perhaps slightly different in size or composition, could be trapped in that frost layer, then released and reworked in spring, with a residual portion settling onto the surface. Over years, such layers are stirred by winds and dust devils. The scrapbook is not neat, but on the flanks of the permanent caps, and in cold traps, there are places where delicate stratigraphy holds on. A future drill could, in principle, find a thin, unusual line, a darker or brighter stripe, enriched in certain metals, a tracer of a single night when Mars caught an interstellar snow. Even nearer the equator, rovers contribute to this diary of small changes. Perseverance's meta-sweet watches, dust opacity, particle sizes, and sky brightness. Curiosity's sample analysis at Mars, SAM, and its tunable laser spectrometer can weigh isotopic ratios in carbon and hydrogen-bearing species with exquisite precision. While neither rover is designed to pluck a single interstellar grain from the wind, they can record the weather of the dust cycle. And, on rare occasions, notice if something in the air feels a touch different. Anomalous aerosol sizes, a faint increase in certain gases that quickly return to normal. It's not a fingerprint, but it's a footprint in soft sand, anticipated and promptly compared against baseline. The question of isotopic breadcrumbs sits at the edge of our ability to claim extrasolar. Ratios like DH in water, 13C12C in CO2, 15N14N in nitriles, or 18016O, can in principle tell stories about where and how ice is formed. If 3I brings a comet-like composition past Mars, and if some fraction of its gas is photoionized and mixed into Mars's upper atmosphere, TGO occultations might place limits on transient increases in those species. But interpretation is delicate. Mars's atmosphere already has its own history imprinted in isotopes, enriched and depleted by escape processes and surface-atmosphere exchange. The background is not blank. Claiming a distinct interstellar signature would likely require a remarkable deviation from the norm, observed in concert with timing, geometry, and other lines of evidence. In other words, possible, but not the likeliest path. Here, too, the science of no is powerful. A formal upper limit becomes a constraint that shapes models of 3I's activity and dust production. How much dust are we talking about? From Siding Spring, models and measurements converged on a very small fluence at Mars, on the order of micrograms to, at most, milligrams per square meter. Tiny, well below hazardous levels, after careful spacecraft maneuvering. An interstellar object would bring its own uncertainties. Its speed relative to Mars could be higher, its dust size distribution different, its outgassing less or more. But for any safe pass, the numbers are still expected to be small, and Mars's global dust cycle is energetic. A single regional storm can lift and redeposit far more material than a cometary flyby will ever add. This is why the memory we seek is not a dune but a dye. Faint, specific, and best seen where the atmosphere itself is a clean sheet. high in the ionosphere, in cold polar layers, or in the spectral lines of rare gases. All of this benefits from choreography. Before the encounter, teams would collect baselines. UNGIMS sweeps through the ionosphere. IUV's limb scans, TGO's occultations sampling dawn and dusk at various latitudes, rovers logging daily dust metrics. During the pass, MAVEN would adjust periapsis timing to catch the predicted peak in ion influx. IUVs would dwell on the limb where the layer is most likely. TGO would aim for occultation chords that intersect the modelled plume. And afterward, we would keep watching, spaced in time to follow the fade. Hours, then days, then a week, taking care not to be fooled by diurnal tides, solar activity, or ordinary meteor showers. Data would stream back to Earth in small bundles that say, here is a rise, here is a fall, here is the quiet return to normal. Not every traveller leaves the same kind of memory. If 3I is largely dry, dusty, but not outgassing, the metal ion layer may be the main event. If it is rich in volatile ices, there might be a brief detection of familiar molecules, CO2, H2O, in the upper atmosphere, or at least tighter limits on their absence. If the geometry is wide and the dust flux low, the memory may be faint enough to hide within the Martian background, and the right scientific answer will be a careful shrug. That answer matters. It tells us that not every interstellar visitor is a cometary fountain. It nudges our population models. It shapes the payloads we design for next time. In each case, the planet teaches us how to listen better. From Siding Spring, we learned to maneuver orbiters safely, and to watch for transient metal layers that mercifully fade within days. From years of routine MAVEN and TGO operations, we've learned how the ionosphere breathes with the sun, how dust lofting ripples through pressure and temperature, how to subtract the planet's own rhythms from a one-night song. The next step is to bring Earth's laboratories into the conversation, to recreate ices and dust in ultra-cold chambers, to measure spectral fingerprints with care, and to let those measurements guide the way we pass the sky, because ultimately, Mars's memory is a translation task. The planet writes down what happened in its own hand, thin lines in the ionosphere. A laboratory can simulate darkness and cold, but it cannot reproduce millions of years. We speed time with higher photon fluxes, and then must be careful to scale our results back down. Our grains are tiny, our ice is thin, our geometry is simple compared to a rough, rotating body, tumbling in sunlight. Our resolve growth, so passages of rise. Still the physics is kind. Vibrations do not lie, desorption obeys its energies. A polarimetric curve knows what shape it likes. With cautious corrections, a chamber's whispered lessons carry out to the sky. There is also joy in iteration. We do not measure once and declare victory. We measure, model, observe, adjust, and return. If 3I's light suggests more CO than we expect at a given temperature, we revisit our mixed ices and ask if pores or salts are delaying release. If Mars fails to find the metal ion layer we predict, we seek smaller grains in the impact lab, particles that ablate higher or slower. Each surprise becomes a new recipe, another entry in the lexicon. And through it all, the lab keeps its bedtime mood. A shutter opens, and we flood the ice with ultraviolet, counting photons like distant stars. A heater nudges the temperature up a fraction of a degree, and the mass spectrometer answers in softly stepping peaks. A polarimeter sweeps its angle and draws a curve that looks almost like a lullaby. Na, Yoda, Ias, Demeta, Sa, Miye. The details, the micrometers and millibars, the per-photon yields, the calibrations, are the quiet stitching. The picture they make is simple, When an interstellar visitor comes, we will know how to listen. We close the valves and let the chamber rise toward air. Frost retreats from the window. Ooh. The pumps soften, then stop. Outside, the night is still. Somewhere beyond Mars, perhaps, a grain of dust spins in the same black we mimic here. If 3i approaches, it will carry ices and stones altered by lights like ours. We'll meet it for a moment with telescopes. And, if we're lucky, with instruments that taste its breath and dust, and because we rehearsed in miniature, under laboratory starlight, the faintest lines it draws across our detectors will feel familiar, like a melody we practiced until our hands could play it in the dark. Chapter 21. Whisper, Finding, Stacking, AI and the Art of the Faint. The night sky is not silent. Asa, Chapter DD, War, Laplas, It has a soft hiss. The glow of air and dust, the grain of starlight, the faint shimmer of scattered moonlight. An interstellar traveler hides in that hush like a single footstep laid on a carpet. To hear it, we do not listen harder. We listen smarter. We put images together like thin sheets of rice paper. We subtract what we already know, and we teach careful algorithms to notice patterns too quiet for a tired human eye. In this chapter, we drift through the gentle craft of finding whispers, difference imaging, synthetic tracking, and the calm partnership between humans and machine learning, made stronger when Earth and Mars listen together. Begin with subtraction. A survey telescope, Atlas, ZTF, Pan-STARRS, and soon Rubin, returns to the same fields of sky again and again, building a library of how the stars normally look. When a new exposure arrives, we make a reference image from past, clear nights and match its optics to the fresh frame. We blur one or sharpen the other so their point spread functions. The precise shapes of star images. Agree. Then we subtract. What is steady vanishes, what is new remains. This is difference imaging, and when it works, the sky's familiar choir quietly steps back so a soloist can be heard. Matching the optics is an art. The atmosphere softens and shivers, the telescope breathes. The detector has its own quirks. Algorithms like Allard-Lupton kernels and the more recent Zogi method learn the correct way to massage one image into the other so that subtraction is fair, not forced. Do it right, and a moving object appears as a tidy point or a tiny streak against a mostly flat field. Do it carelessly, and the stars leave dipoles, little positive-negative pairs that look like ghosts of themselves. These ghosts are tempting to chase, so our next step is to become very good at ignoring them. Even without subtraction, the object's faintness would be a problem. A single 30-second exposure might show nothing where the traveler is, just noise with a few random bright specks. But we rarely take only one exposure. We take a train of them, evenly spaced, and then we lean into time. If the object is moving, we shift each frame so that a hypothetical traveler at a particular speed and direction would line up perfectly from one image to the next. Then we stack. Stationary stars blur, the traveler's light adds up. The signal grows as the square root of the number of frames, while the noise meekly follows, and a dim dot that hid in the grain of any one image becomes a small, confident bump when we layer the set. This shift and stack, or synthetic tracking, is as soothing as it sounds. Try a velocity, align, add look. Try another, align, add look. We sweep a small grid of possible motions, tens to hundreds of trial vectors, maybe more if we are ambitious, each time asking the same soft question. Do we see a point-like shape at the end? On fast hardware, this is surprisingly peaceful too. The camera gathering frames in the dark, the GPU aligning them at quietly different speeds, the software returning small cutouts, each a patch of sky with a hint or no hint at all. where we expect 3i might be. Guided by early astrometry, we search more finely. Elsewhere, we keep the grid course. Oyu as za, the Korean for the EU. The trick is not to get lost in our own effort. Searching many motions means more chances to fool ourselves, so we budget our false alarms and ask for a stronger bump when the number of trials is large. Some visitors don't point their light, they drag it. When exposure times are long, a fast mover draws a slender streak across the detector. That streak is a signature too. We can look for it with algorithms that prefer lines, Ho transforms that take a noisy image, and ask which straight paths have too many bright pixels to be random. Or we can match filters shaped like a streaked point spread function, tilted to different angles, and see which angle answers back. A real streak carries its own propriety. Its ends are not too sharp or too blunt. Its brightness is even. Its direction matches how the sky would blur at that moment, given the Earth's rotation and the object's motion. False streaks, satellite trails, cosmic rays, sensor scratches often fail these manners tests, and we gently show them out. The work doesn't end at found. We need to link detections across nights to a single, coherent path. The association problem is calmer than it sounds. A handful of dots in a handful of images, connected by the simplest kinematics. Software builds tracklets, short strings within a night, and then links tracklets into longer arcs across nights, allowing for the gentle curvature of orbits and the uncertainties in where exactly the object was. Elegant data structures, KD trees and friends. Let us try combinations quickly, pruning unlikely pairings without breaking a sweat. A real traveler's path looks smooth and plausible. A spurious chain usually kinks or jumps, and the algorithm learns to frown. Still, the sky is generous with distractions. Cosmic rays strike the detector and make single frame spikes. Satellites leave broad trails. Hot pixels pretend to be stars. Thin clouds add blotches to the background. To sift wheat from chaff, surveys long used real bogus classifiers, small machine learning models that look at postage stamp cutouts and decide whether a detection smells like the sky or like a glitch. Modern versions use convolutional neural networks trained on millions of examples. They learn the rounded shoulders of true point sources, the telltale negative lobes of bad subtractions, the texture of cloud softened fields. They are apprentices that memorize our habits and help us move faster. We keep them honest with human eyes. Active learning loops invite people to judge the examples the network is most unsure about. Those labels go back into training, and the apprentice improves in exactly the places it was weak. We also look under the hood. Saliency maps and other interpretability tools show which pixels the network cares about. So we know it is looking at the source and not at some unrelated blotch in the corner, and we test constantly with injections. Faint sources we add to the data stream without telling the classifier, so we can measure how often it finds our planted whispers, and how often it invents whispers we never put there. Completeness and purity become bedtime stories we can tell in numbers. One of our gentlest advantages is stereo hearing. If Earth and Mars both watch, even briefly, the same object on the same night, their very different vantage points draw a bas-relief instead of a flat sketch. Parallax shifts the apparent position by arc minutes or more, when the baseline is tens of millions of kilometers. Two sets of images, timed with care and tied to the same star catalogue. Gaia's precise map lock the object's distance much more quickly than Earth alone could. That early distance breaks degeneracies in the orbit fit. We learn not just where the traveler is and how fast it moves across our field, but how fast it is coming toward or away from us. The result is not just a better ephemeris. It is time returned, time to schedule telescopes, to swing spectrographs toward a narrow slit, to cue MAVEN and TGO for coordinated glances. All of this happens to a rhythm. A candidate appears in a difference image. Synthetic tracking lifts it above noise. The pipeline measures its position and brightness with tidy uncertainties and pings an alert broker. The broker, software that collects and distributes candidates, fans the news outward to astronomers and to allied machines. Observers ask their telescopes for target of opportunity time, a brief, negotiated interruption of planned observations to take a look while the look still matters. JWST can pivot to near spec or new cam, HST to WFC3, large ground-based mirrors to high-resolution spectrographs, or read ruts attitude distorts. On Mars, MAVEN can slide a periapsis, TGO can adjust occultations, and even rovers can tilt cameras skyward for a few minutes at dusk. If the signal fades, we do not panic. We downgrade the plan gracefully. Spectroscopy is greedy. It needs a lot of light. We fall back to broadband photometry, to polarization, to astrometry, a few precise positions that keep the ephemeris healthy. Non-detections flow back into the model as upper limits, gentler lines that still shape the picture. The pipeline keeps watching, keeps stacking, keeps whispering to itself, waiting for a small bump to reappear above the grain. We resist chasing noise. Our patience helps. There are small practical kindnesses we pay to ourselves. Every frame must know its time, down to fractions of a second, so we can correct for light travel delays and for the Earth's and Mars's motion. Every position must be tied to Gaia's catalogue, so that astrometric residuals tell the truth. We learn our detector's quirks ahead of time. Where fringing hides, how dark current creeps, which columns misbehave, how scattered light slips around the edges. We mask and model without drama, so that the difference image is clean not by miracle, but by design. Calibration lamps glow, flats and biases collect like quiet chords, and the pipeline warms up before the night, so it can hum along with few surprises. What we gain from all this is not only discovery, it is confidence. When the call comes, a faint moving point near Mars's path, we will have a suite of tested ways to say yes or no. We will know how to catch the dot, how to keep it between our fingers as it crosses the field, how to pass it from one instrument to the next without dropping it in the dark. We will have practice explaining why we think it is real, how we measured it, what we plan to try next, and what we will do if the next image is quiet. The galaxy will send more wanderers. Some will shout. Most will whisper. By layering frames, subtracting the known, and giving our patient algorithms the right habits, we make room for the quiet ones to be heard. And when Mars joins in, offering a second ear across a vast, calm baseline, the whisper becomes a voice, just long enough for us to learn its tone. Thank you for keeping me company tonight, as we traced a quiet path from an interstellar visitor to the red hush of Mars. If your eyes are heavy, let them close. Let the questions stay warm and unresolved. If you drifted off and woke up here, that's perfect. If you're still awake, you can let the playlist carry you to another calm corner of the cosmos, or simply rest with the music a moment longer. For a nightly lullaby of science, you're welcome to subscribe and set a gentle reminder, so your seat is waiting when the stars return. And if a thought from tonight made you smile, leave it in a soft comment. I read them in the quiet hours. Sleep well. Class resumes tomorrow night. Meet me here for another quiet chapter with the sleepy professor.